We've talked about what the definite integral is. Now we're going to look at some properties of the definite integral. And so to start with, it's a little bit of a review again of how to evaluate a definite integral. So here we have got the integral from 0 to 3 of 2x minus 6 dx. I took a pretty simple function, and that's what's graphed here. This would be the line 2x minus 6. So, it's got the point here, 3 comma 0, right? If I plug 3 in for x, I get 0 out. And I got the point 0, negative 6 down here. If I put 0 in for x, I get negative 6 out. And it turns out if I'm evaluating this integral, I really would be, I'd be going to this function from the x-axis. And what would be different here is when I do these little rectangles, they're going to be going downward instead of upward. And my function values are negative when I'm putting in these x values. So let's see what happens as I go through this then. So the definition of a definite integral is this: the limit as n goes to infinity of this Riemann sum. And x sub I star, remember, is a sample point in each little subinterval. And so since my function here is 2x minus 6, that's my f of x here. Then f of xi star, I just plug x sub I star in for x here. So 2 times x sub I star minus 6 times delta x. We can always use these formulas for delta x and x sub I star. I talked about that in the mini lecture about just the definite integral. And so for our value here, we've got that a is 0 and b is 3. And so b minus a over n would be 3 minus 0 over n, which is just 3 sub n. And then x sub I star is always a plus I times delta x. My a here is 0. My delta x we just found here is 3 over n. So I just get 3i over n. So now I take these values, x sub I star and delta x, and those get plugged in up here, right? So x sub I star gets plugged in there, and delta x gets plugged in there. And that's where this comes from, right? So instead of x sub I star, I put 3i over n. Instead of delta x, I put 3 over n. And then I just do some algebra. 2 times 3i is 6i over n. Then I distribute. 3 times 6i is 18i. N times n is n squared. 3 times 6 is negative 18. It's over n. Instead of the sum of this difference, I can do the difference of two sums. So I just break them apart into 2. And then anything that's not involving an I is a constant as far as this sum is concerned. I'd be able to factor it out essentially. So that's where this 18 over n squared came from. And here I'm just going to take out, I'm going to leave the 18 and just take out the 1 over n. And so now we talked about these summation formulas. I can evaluate this sum here and this sum here using these summation formulas that we talked about in the other lecture. So again, if you look at the lecture about the mini lecture about the definite integral, we talk about those formulas, and that's what happens here. So this is exactly what I've got here. Instead of the sum, I goes from 1 to n of I, that's just n times n plus 1 over 2. And the sum as I goes from 1 to n of 18 is just 18 times n. And so now I just do some cleaning up. I distribute the n here and get n squared plus n. Here these n's cancel out. Right? Those n's cancel. And then I distribute 18 times n squared is 18n squared. N squared times 2 is 2n squared. 18 times n is 18n. N squared times 2 is 2n squared. The minus 18 just goes along for the ride. Here then, these n squareds cancel out entirely. So I just get 18 over 2 is 9. Here, one of the n's would cancel, so I'd get 18 over n minus 18. And then as n goes to infinity, this is 18 over a huge number. 18 over a huge number is essentially 0. So I get that this whole integral, this definite integral at the beginning, would have a value of negative 9. All right, let's talk about that a little bit. So we defined the definite integral the way we did in order to find the area under a curve. And so we expect that the definite integral should be giving me an area. So what does it mean that our answer here is negative? Well, notice that this is a right triangle, right? The area of a triangle is always 1/2 base times height. For this triangle, we could actually use the idea here that the base b is equal to 3, and my height is this distance here, right? So I've got my base and my height. And the area then, 1/2 base times height, would be 1/2 times 3 times 6, which would be 9. So the area of this shaded region is 9, but the value of the definite integral we found is negative 9. So it seems that if I've got an area under the x-axis, that has a negative value when it's evaluated with a definite integral. And we can prove that that's true. It really has to do with these, the Riemann sum and the way that's formed, and the fact that my rectangles would be going down and they would have negative heights. So that's the reason we get a negative area for that. So if we evaluate a definite integral for a general function, just over a general closed interval from a to b, the resultant is not necessarily the area under the curve. This will be true if the function is positive for all x coordinates in the interval. But that wasn't the case up here. So if the function is negative for any x coordinates in the integral actually represents the difference of the area below the curve but above the x-axis and the area above the curve but below the x-axis. I know that sounds a little confusing. This picture really shows what would be happening here. If I took essentially this same function, 2x minus 3, 2x minus 6, and if I looked at it all the way from 0 to 5 instead of 0 to 3, when I would evaluate these Riemann sums, we would get the little rectangles, they'd be going down, in this red portion, but they'd be going up in the blue portion. So I can say that this blue area, A1, that's a positive area, whereas A2 here would be a negative area. And if I calculate these areas, again, it's just 1/2 base times height. So the blue area here, A1, has a base of 2 from 3 to 5, and a height of 4. It goes up to this point 5, 4, right? If I plug 5 in for x, 2 times 5 is 10, 10 minus 6 is 4. So, this point up here is the point 5, 4. And so it's got a base of 2 and a height of 4. So 1/2 times 2 times 4, that's just going to be 4. We already found this red area before up there, that's 9. But to do this whole integral then from 0 to 5, it would be the positive area minus the negative area. So the positive area A1 is 4. The negative area A2 is 9. 4 minus 9 would be negative 5. And that would be the value of this integral. Okay? So, as an example then, let's say I've got this function g of x. I want to use this graph to find the value of each definite integral. So here, we've got the integral from 0 to 30. So that's letting x go from 0 to x equals 30. And if I'm evaluating that integral then, I'm going to be finding the area under the curve but over the x-axis between those values, okay? So if I look at that as an area, what am I going to get as my area? Well, these are squares, so I'm going from 0 to 10 and 10 to 20 and up 10. So the area of a square is just length times width. 10 times 10 is 100. So those squares both have areas of 100. These are right triangles. I could do 1/2 base times height. That would be 1/2 10 times 10, right? But that's just going to be 50. And of course it's like, well, duh, it's half the square. So this is 50, this is 50, this is 50. So this total area then from 0 to 30 would be 100 plus 100 plus 3 times 50, 100, 200, 350. So that would be the integral from 0 to 30. Now, if I want to do the integral from 30 to 60, that would be starting here and going to here. Again, these are squares. This would be negative 100, right, because it's below. These would then be negative 50 and negative 50. And so this area would be negative 50 plus negative 100 plus negative 50. And so that would be negative 200 would be the value of that integral. And if I'm going to do the area from 0 to 60 then, well, I know this area is 350, and I found this area was 200. And so this total area for the integral, I take the positive area and I subtract the negative area. So it would be 350 minus the 200. So it would be a value of 150. So some properties that the definite integral has, and these can all be sort of thought of in terms of what this integral means as an area, and we can use that to sort of deduce these properties. There are more theoretical proofs of these properties that I'm just not going to get into here. These informal, we've got sort of an informal proof of the ideas that's probably good enough for what we need to do. So when we originally defined this integral from a to b, it was sort of an assumption that a then is less than b. I'm moving from left to right. But that actually doesn't have to be the case. Now, if I switch a and b around here, then when I do delta x when we calculated that before was just b minus a over n. That's the total length of the interval, the distance from b to a, from a to b, divided by n little subintervals. If I switch the b and the a, it changes from b minus a to a minus b. Well, switching the subtraction means I get the opposite sign, right? 10 minus 2 is 8, 2 minus 10 is negative 8. So delta x would change signs, and what that really does then is it just changes the sign of the answer. So if I'm going to integrate from b to a instead of a to b, it's the same as the integral from a to b, I just have to multiply the value by negative 1. So the integral from b to a is the opposite of the integral from a to b. Okay? Sort of like that, if a is equal to b, then when I subtract a minus b to get delta x, I get 0. So delta x would be 0. And of course, that's leading to this property. The integral from a to a of anything is equal to 0. Of course, from a function point of view, you know, essentially, if I would have from a to b, that would be this area. But as I let b get closer and closer to a, this area gets smaller and smaller until if b becomes equal to a, there's no area anymore. So that the value of that integral is equal to 0. If we integrate a constant function, f of x equals c, then the integral from a to b of f of x is just the integral from a to b of c. However, think about this graph. If I have f of x is equal to c, the graph of that function would just be y equals c, which is a horizontal line. And if I'm doing the integral from a to b, then I'm finding this shaded area. But this is just a rectangle. The shaded area here, well, what's the distance here? Going from a to b, that distance is just b minus a. And so that's where we get this value right here. The integral of a constant is just the constant times the length of the interval. Okay, so my constant c times b minus a. Because the definite integral back there was a sum, right? It was the limit of a sum. If we look back here at all this crazy work, this integral is just the limit of a sum. Okay? So anything I do when I'm adding, I can do with integrals. In particular, we can always factor out a common factor from a sum. If every term has a common factor, we can factor that out. Or we can rewrite the terms in whatever order we want. So these properties come from that. If I've got a constant times a function, I can just pull the constant out of the integral. Okay? It's really like factoring it out of the sum. Okay? Also, if I'm integrating the sum or difference of two functions, I can just take those integrals separately. One important note, this doesn't work if I'm multiplying or dividing functions, only if I'm adding or subtracting. And then finally, because this definite integral represents an area, we can split the area of one big region into smaller regions and get a result like this property here below. We're assuming that A is less than C is less than B in this picture. So instead of going all the way from A to B and finding the total area, I could calculate the blue area from A to C and then the yellow area from C to B. So instead of integrating from A to B directly, I can go from A to C first and then C to B second and just add those results together. So these are properties we're going to use throughout the rest of the course. You'll become more familiar with them as we go through some stuff here. Here's a couple examples of what we could do with this. So if I'm given that this integral from 2 to 10 of f of x is equal to 12, so I don't know what the function is, but that's the value. How can I evaluate then this integral here? So first of all, that's the difference. I can write that as two integrals. I can go 2 to 10 of 6 dx minus integral 2 to 10 of 2 f of x dx. Okay, now this is just the integral of a constant. So the integral of a constant, right, that's that idea. I have a constant like this, and I'm going from A to B. So what's that area? Well, this is my constant 6, right? That's my y-coordinate, 6. And I'm going from A to B. That's going from 2 to 10. And so my value is just 6 times 10 minus 2. Right? The distance from 2 to 10 is 8. So it's 8 across and 6 up. That's what we're getting here. Here I've got a constant times the function. I can pull that constant out of the integral. So I'm going to get minus 2 integral 2 to 10 f of x dx. So this is 48, 6 times 8. Minus 2 times the integral from 2 to 10 of f of x dx. That's what we had up here. So the integral from 2 to 10, that's just equal to 12. So I'm going to get 48 minus 24, and my answer is just going to be 24. All right, now one other example. Let's say we have this integral from 2 to 10 is still 12, but now I know the integral from 6 to 10 is equal to 3. Can I find the value of the integral from 2 to 6? Well, sure. I mean, this is that idea we were talking about here. There's 2, there's 6, and there's 10, and I would have some integral. Well, I can do the first area plus the second area to get the whole area. So I know if I do the integral from 2 to 6 f of x dx plus the integral from 6 to 10 of f of x dx, that would be the integral from 2 to 10 of f of x dx. Right? I would just, if I do this area plus this area, it would be the whole area. And I know some of this. 2 to 6 I don't know. I'm given that the integral from 6 to 10 is equal to 3. And I'm given the integral from 2 to 10 is equal to 12. So I can just solve this equation. I subtract 3 from both sides. 12 minus 3 is 9. All right, a couple more properties. Don't really have any example problems for these, but properties that are going to make some sense here, and every once in a while it's important to sort of realize this. These are going to be more important when I do some calculations later on. First of all, if I do have a function f of x that's greater than or equal to 0 on the interval from a to b. So that means f of x never drops below the x-axis. Well, in that case, then this definite integral is the positive area, so the definite integral itself has to be greater than or equal to 0. Right? So if my function is always greater than or equal to 0, then the integral has to be greater than or equal to 0. Second, if I have two functions here, f of x on the top, g of x on the bottom, and if they have this relationship that one function is always greater than or equal to the other, they are equal where they touch here, but that's okay. What this means then is the integral of f of x, the top function, has to be greater than or equal to the integral of the bottom function. And of course, that makes sense if you think about this in terms of area. The area under g of x is part of the area under f of x. So the blue shaded area has to be less than the area under f of x. So the integral of g of x has to be less than f of x, or the integral of f of x has to be greater than or equal to the integral of g of x. And this last property, if I have a function f of x whose values stay between a little m and a big M, so little m is like the minimum value of the function, capital M is the maximum value of the function. Okay, so little m is minimum, capital M here is maximum. And that's what we have here, my little m and my capital M. My function f of x reaches capital M here and little m here, and those occur between a and b. But as I go from a to b, f of x stays in that band. All the y-coordinates stay between little m and capital M. Well, then that means the value of my integral, remember that's the area under the curve, has to be between little m times b minus a and capital M times b minus a. All right, now that's not really that complicated. These are just areas of the rectangles that we would get in the picture here. So little m times b minus a, that's this distance here. Little m times b minus a is this darker blue area at the bottom. Capital M times b minus a would be the area of the big rectangle. And the area under the curve has to be between those two values. It can't be less than this blue area, right? There's function above this line. So the total area under the curve has to be bigger than this little area, but it has to be less than the bigger area. And so we get that result. And these properties of integrals are going to turn out to be important as we do more advanced problems in calculus.